Morning, everyone. So, yeah, certainly helps to have a larger room, eh? There's a chair up front or two for those who are interested, and of course, some hanging out on the side. So, do we have any questions from the last couple of classes? Yes.
This is a question more about logistics.
May I have your tag, please?
Yes. Andrew, it's my name.
And,
Is the collaboration policy on the quizzes the same as the homeworks?
so we don't mind you discussing things with one another, but all of you are supposed to answer the quizzes and homeworks individually, right? I mean, the point is for you guys to learn. On the other hand, if you're copying somebody else's answers, you're guaranteed not learning anything, right? Discussion helps, copying doesn't. Anybody else? All right. Yes.
For the quizzes, there are 2 allowed attempts. For the current setting, it seems that the grade is based on the last attempt.
So for this particular quiz, we are going to sort of use the best attempt simply because we had a lot of people are still kind of getting used to Canvas, and many people attempted, just looked up the questions and ended up registering a bogus score. But yes, we're sort of we're going to be using the last score for a very simple reason. Just think of the limiting case. If I gave you 100 tries, and if I chose the best one, everybody's going to get a 10 on 10, right? It doesn't make sense. So we are letting you update your score, but the point is you're supposed to be thinking about the quiz answers, not gaming your way through the quiz. Yes?
What is the grading algorithm? So like, when you get half points, what does it mean?
Pardon me?
When you get half points, like how is that calculated?
When you get half points, what do you mean by half points?
Like a half of a point.
A half.
On the quiz?
Yeah, in the quiz, well, they're just going to get accumulated, right?
Yeah, but like when you get 0.5,
Uh-huh.
how is that calculated? So when you have multiple choices.
So if you have, say, 2 choices, then you're going to get a half point for every correct choice that you selected, and a minus half for every wrong choice that you selected. So in principle, it's if I give you a multiple choice question where there are 5 choices and only 1 is correct, you're fully capable of not only getting a 0 for that score for that question, but wiping out the scores for a few other questions besides. Yes. Anything else? Again, we're not being mean, right? The whole point is we're trying to make sure that you go through the material and you're giving us an honest answer or honest best guess for your answers and not gaming the system. Again, the intention here is for you to learn, and we're going to try to quantify. There are chairs over here if you're coming in. All right, guys, let me begin. So, topics for the day, we are going to be going over for the next several classes. We are going to be talking about learning a neural network. So we're going to be looking at the basic problem of learning. We'll spend a lot of time trying to understand perceptrons, because perceptrons are the basic unit that we're actually going to be, that we build our networks with. And we will see in the process why the simple problem of learning perceptrons doesn't generalize to multi-layer perceptrons, why we need more advanced answers. We'll look at greedy methods of trying to learn neural networks, and go through the basics, the basic empirical risk minimization approach that we will actually be using to train the networks. Quick recap. Everybody recollect this, right? A neural network can model any Boolean function. Does anybody have any? Yes?
Can we use this?
On the right side. Both of them.
Yeah, point is I was going to actually write on the board. So that's why I needed the only one. I mean, if we had a board on the side, I could use it, but unfortunately we don't, right? So we saw that a neural network can approximate pretty much any Boolean function, right? We also saw it can model any classification boundary. Now, after the last class, several students had questions about the cylinders and all the other figures that I drew. Did everybody understand those? Or any questions? How many of you actually were in the class or saw the video? Okay. I see a couple who didn't. Right? So you guys, if you have questions, post them later. And the next time I ask this question, I expect all hands to be raised, and those are, honestly. So we also saw that a neural network can model any continuous valued function. And this last bullet was most important. Provided the network satisfies minimum architecture constraints. What did I mean by this? Anyone? So we went through this in some. Let's see.
That the model architecture is sufficient for the task at hand.
So we actually had a way of quantifying this, right? That you must have a minimal number of layers, and you could always truncate for any number of layers. Firstly, we saw that a neural network with just one hidden layer can approximate any function. But if we tried to do that, how many neurons would we need in that one hidden layer? Potentially infinite, correct? So we could reduce the number by increasing the depth. But if we fix the depth of the network, what was the upper bound on the number of neurons you'd require? Once again, infinite. So anytime you try to build a network in the AC0 class, basically a fixed depth network, there really is technically no upper bound on how many neurons you're going to require to actually compose an arbitrary function. But then, provided we have a network, even if we have a network of sufficient depth, if I limit the number of neurons in any particular layer, are we guaranteed to be able to model any function? No, we saw that's not really true, right? So basically, when I speak of a network of sufficient architecture, it has a sufficient number of layers, it has a sufficient width at every layer, and the entire structure has the ability to model a specific function. Now, we are speaking of ability to model a specific function. It doesn't necessarily mean that just because it's able, it will model the function, and we will see what I mean by that, right? So we saw that all of these boxes, basically, for all of these tasks, they're just functions. They take an input, they produce an output, and these can be modeled using neural networks. So now what we're going to see is, okay, fine, we decided these are functions. Functions can be modeled by neural networks. How do I compose a neural network to compute this particular function? Now, for this, here we have the basic operations where we saw were fairly abstract. Something bizarre went in, like text or a picture. Something bizarre came out, like a caption or the next game state. Now, when we are speaking of functions, we're really speaking of things with numbers and digits and things like that. You can't, So if I want a neural network to operate on a game state, the game state has to be converted to sets of numbers first, right? So first question is, how do we represent the input as collections of numbers? How do we represent the output as collections of numbers? And then once we've specified these two, how do we compose a network that converts this input to this output, right? So we're going to go over how we represent the input and output a little bit later. We will actually focus on the second part for the moment. How do we compose a network that performs the requisite function? So we're going to live in the abstract. Inputs are collections of numbers, outputs are numbers, okay? Now, the basic unit in the network we saw was the perceptron, which has this structure. You look at a weighted combination of inputs. You add in a bias. So now you get an affine combination of inputs. Remember, we discussed the distinction between affine and linear, and the distinction lay in the bias term, right? And then we have an activation function that operates on this affine combination of inputs. And this activation function in the most basic case that we saw, the perceptron as it was originally defined, this was a threshold function or a sign function. You just looked at the sign of this z, and if the sign was positive, you output a 1. If the sign was negative, you output a 0 or a -1, depending on the convention that you chose, right? But we could replace this activation by other kinds of soft activations, things that change continuously, like a sigmoid, or this half-wave rectification function, or the smooth version of it, various other options. So activation functions are not necessarily threshold functions. Now, during my lectures, I'll make sometimes anytime I speak of a perceptron, you have the affine combination of inputs that goes into the activation function is a weighted combination of all the inputs plus a bias term, right? But then writing things like so can get very tedious, right? Every time I have to write a plus b. So I can take a shortcut. I can just add an extra 1 to the vector input and pretend that this is an extra component that my input has, in which case my bias is simply going to become this weight. That clear to everybody, right? So when I write it when I re-represent it in this manner, I can just write z equals the weighted combination of inputs. But this really is not a linear combination. It's still an affine combination. I converted an affine to a linear by just adding an extra 1 at the bottom and treating the whole thing as a linear combination. So this is a shortcut that we will frequently use anytime in any of my figures, anytime I write something of this kind, there is always a bias term, right? If I forget it, you cannot forget it. Every single unit, every single perceptron that we will ever see in class from here unto infinity or the end of the semester, whichever comes first, is going to have a bias term, right? Unless I explicitly tell you that it doesn't. So here's how we're going to represent it. Now, the structure of the network, we saw that we're going to consider feed-forward networks. What do I mean by a feed-forward network? Look at this structure, or this one. Some input comes in, it gets operated on by these units. Their outputs get operated on by these units. Their outputs get operated on by these units, and so on, all the way down. The signal never goes back to any unit, right? So when the network is operating on any particular unit, once it's processed it, any particular input, once it's processed the input, it forgets about it, because that doesn't go out and then come back through some other path back to the unit. So this is a feed-forward network. It's directed. All the computation is directed and acyclic. So this is the kind of network that we're going to be talking about. Here you have a network with many outputs. Here you have one with just a single output. So this is we will be talking about loopy networks where the computation comes back to a perceptron later in the course, but that's not going to be the topic for the next 5 lectures. So part of the design of such a network is the architecture. How many units does it have? How is it connected? How many layers do they have, etc. For now, I'm going to assume that the architecture of the network is capable of representing the target function. Mind you, we're trying to learn a function, right? So we're going to assume that the architecture is capable of representing the function. So overall, here's the situation. Our network is really just a function, right? It takes an input, it produces an output. What is that? That's just a function. But this is a function with parameters. And what would the parameters of this function be? Anyone? All the weights and the biases of the neurons. Basically, all the numbers attached to these blue arrows. So when I'm speaking of learning a network, what I'm really speaking of is learning the parameters of this network such that it performs the operations I really want it to perform. So, questions so far? This was just a recap. No? Okay, let's move on. So here's where we stopped. We said the multi-layer perceptron can model any function, right? But can is not the same as saying does. Capacity is not the same as saying, ability, right? So I have the network, and let's assume this network actually is capable of representing this function. This is the input x. The gray mesh represents the value that the function must take at every x. And I want to compose this network such that when I give it any x, the output for that x is going to be whatever is given on this gray mesh, right? This is what we mean by composing a function. So how do you do it? Simplest thing, I can try to hand design my network. We saw how we can hand design networks if we want outputs of this kind. I want the output to be 1 inside the diamond, 0 outside. Then I know the exact architecture. I need 4 neurons, 4 perceptrons in the first layer, 1 for each of the 4 lines. And then I need a final one to perform an and I can do it. It's trivial for something as simple as this. If I make this even just marginally more complicated, this is not going to work, right? So more generally, what we are speaking of is we have a function, some g of x, and let's assume we're given the function g of x. We want to derive the parameters of this network such that, and what are the parameters of this network again? The weights w, right? So the weights include the biases. I'm not explicitly specifying the biases. So we want to derive these weights w such that at every input x, the output of this network is going to be whatever is given in this mesh, g of x, right? So let's say I want to do this before I move on. How would you do this? Anyone? So I'm given a function. I'm giving you a parametric form for a function, and I'm telling you what function it must emulate. So what am I really saying over here? The question I'm asking you is, how do I learn the weights w, or what must I set the weights w to be such that this network computes the function to the right, right? And I'm giving you the function. So in that case, how would you do it? Pardon me?
Sample some points as the input and the output.
We're not even getting, I'm giving you the entire function, right? Yes.
You take a shot and then see how far your function is from the function that you're supposed to emulate.
Okay, and?
And then you correct. So if you have to lower your weights, you do.
Okay, so mathematically, how would I do this? If I want to, okay, what is the first thing I have to define? By g of x is given, right? Assuming g of x is given, what is the next thing I would have to specify?
How to estimate to compute the difference.
How to compute the difference if I don't know, if I don't have a way of quantifying the error between, so here's what I would have, right? It's a nice fat chunk. So I'm assuming this is a scalar function for now, right? So this, and let's say this is g of x, right? For any specific setting of w, I'm going to have the network is going to compute some function, right? And that's not necessarily going to be g of x. So I give you some w, and if I, for that w, maybe the network computes something like this. Right? So if it does so, then this, guys, this is all error, right? That entire range of values, that area represents the error that the network would actually the error in the output of the network over the entire space of inputs. So I could now have, say, another function. I have another color. So let's say I have a different setting of w, and the different setting of w gives me something like this. So what would the error now be? The error now is going to be this guy, right? So what am I trying to do when I'm trying to learn that function, that network to the left? I'm trying to minimize this area. I want to set it to be as close to 0 as possible. But to do that, what is the very first thing I need to do? Pardon me?
Domain.
Okay, I have a domain, and I need a way of quantifying this area, right? I need to specify how I compute the error. And so and then you're going to tune the w such that this area is minimized. So we're going to have, at every point, the way you would do it is at every x, this is the value that you want. So let's say the purple function is the purple curve represents the current function. So this is the actual the value that's currently being computed. So you need some way of quantifying this gap between the two, right? And I'm going to call that way of quantifying it div. It's a divergence function. The divergence function tells me the difference between the value of the output of the network and the value that I really want at each x. And so what is this integral doing? What would this integral be? Okay, firstly, what do you want for the properties of this divergence? Anyone?
It is equal to g of x, then
If it's equal to g of x, it must be 0. Anything else? So look at this guy. Here, the error is in this direction. Here, the error is in this direction. Do you want them to cancel out? No. So what must the divergence look like? Regardless of the direction of the error, it's got to have a non-negative value, right? It's some kind of, or some way of things. Doesn't necessarily have to be non-negative, but it has to be some number that actually accounts for the overall area and doesn't let positives and negatives cancel out. So we have a divergence of this function of this kind. This integral is the entire area as specified by the divergence. Now the divergence is not just the absolute difference. There are different ways of quantifying the difference between the two, right? Whatever it may be, and we'll see how we can, what are the different options for a divergence. But still, conceptually, that's what you're trying to minimize. And we are going to try to find the W that minimizes this divergence. Problem, in real life functions, when I'm trying to say, here is an image, give me a caption, right? That's a function. For you to be able to use this mechanism for learning a network that computes that function, you need g of x all over x. You need g of x at every single point of x. And do we have it? Not really, right? G of x is unknown. And for us to use the other mechanism, g of x must be specified everywhere, and we don't really have such a specification. And so what we will do, who was it who specified? Was it you? No. Okay, you. So Yi-Chen, you are the one who mentioned sampling, right? So we won't actually have the function x everywhere, g of x everywhere. Instead, what we will do is pick some values of x and compute the value of the function at those x's. And now, basically, what we are going to do is sample g of x, get input-output pairs from the function g of x. And this is possible for pretty much all of the problems that we saw, right? I mean, think of the problem of trying to generate captions for images. What does it mean to produce a sample? It means I get an image and I get its caption. That's a sample, right? The business of recognizing speech, what does it mean to generate a sample? I get a recording, speech recording, I get its transcription. That's a sample. So it's possible for me to get samples from g of x without knowing all of g of x. In fact, that's exactly what we're going to do all the time, right? So now the actual sample that you get, very often you won't really get the desired target output. You're going to have some noise in it. Most times, the mere act of observation is going to introduce noise in whatever you saw. So in that sense, think of the samples that you get as the actual value of the function that you'd have liked to get plus some noise. So we're going to have a collection of these guys. And from this, we're going to try to learn the function. You have lots of those samples represented by the lines, each of which is an x and the corresponding d rather. And we will try to learn a network that computes those input-output pairs correctly and hope that in the process, we're actually going to learn the entire function to the left. So we must learn the entire function, the entire gray mesh, based only on those sampled values, and these are what we'll call our training instances. This is what we're going to be learning the network from. Questions? Yes?
You said the mere act of observing the data might change it. Could you elaborate on that?
So we are speaking of adding some noise. Now, there are different ways of explaining this. The function is not unique, right? And we'll quickly see what I mean by that in a few, if you wait a little bit. The way I plotted the function, at any given x, there's a unique output g. That's not always going to be the case. So think of, I can come up with examples. It'll begin sounding hokey, so let's just wait a bit, right? So what we want to do is to learn network parameters to fit the training points exactly, assuming that the network architecture is sufficient for such a fit. And we are assuming a unique output D at any x. That's the assumption we are making for now. And this might mean that for every, so to answer your question, your Shonak, okay, I can't really, you should write it bigger, right? So very often you will find input-output pairs where for the same input you get multiple outputs, right? So the relationship that you get in your training samples is not going to be unique very often, which is what I'm characterizing by the noise over here. But for now, we're going to assume that in our in the data that we got, this relationship is unique. At any x, you're only going to see a unique D. So here's the story so far. Learning a neural network is the same as determining the parameters of the network, which are the weights and the biases, required for it to model a desired function. For this, of course, the network must have sufficient capacity to model the function. Ideally, we would like to optimize the network to represent the desired function everywhere. We want to do this, right? In practice, you're not going to have the function g of x everywhere. So what we will do is to draw input-output training instances from the function and estimate the network parameters to fit the input-output relationship at these instances. Yeah? So let me begin with a very simple task. Again, neural networks can be Boolean functions, they can be classifiers, they can be real-valued functions. I'm going to start with a classifier because it's much simpler than regressions. And also because historically, when people first began working with perceptrons and multi-layer perceptrons, the initial attempts were Boolean functions, but the next thing were, of course, classifiers. So it kind of fits into the history. Specifically, we're going to consider binary classification, and this will generalize to multi-class classification quite trivially. So here's the original MLP again. Now, this was the original perceptron as proposed by, who was it? Rosenblatt, right? And Minsky was the one who supposedly said you can connect these things up in a network and compute more complex functions. So here is the MLP as originally proposed by Minsky. And the question is, how do you train it? So what is the simplest MLP? The simplest M doesn't have an M, it doesn't have an L, it only has a P, right? So the simplest MLP is just a perceptron. So let's see how we're going to train a perceptron. Now, what is the kind of function a perceptron actually captures? Just to help you, I have the figure over here, right? I have a perceptron has a linear boundary. On one side of the boundary, it's going to output a 0. On the other side, it's going to output a 1. So that linear boundary is basically just a hyperplane. In 2 dimensions, that would be a line. So if the input were 2-dimensional, the perceptron is going to be a function of this kind. It's a step function across a hyperplane. And this is what we want to learn, but we are not going to be given the entire function and say, nobody's going to give you the step and say, OK, find me the perceptron that computes the step. What we will have is something like this. You're going to have a collection of blue dots, some instances where the output value is 0, other instances where the output value is 1, and we have to learn the weights over here and the bias such that the resulting perceptron produces an output of 1 for these red guys and 0 for the blue guys, right? And so how would we do this? This is basically the problem that we've got. You're given a number of input-output pairs. You want to learn the weights and the bias such that it satisfies this. Now, this is the equation of the perceptron, right? If the weighted combination of the inputs and the bias is positive, the output is going to be 1. Otherwise, the output is going to be 0. And we want to learn these weights and biases such that when this relationship is satisfied, the output is 1 for these red points and 0 for these blue points. I made a mistake in my slides later. I kind of flipped the colors, but bear with me, okay? So let me restate the problem. I'm just getting rid of the bias. I'm just adding by appending a 1 over here, and the bias has just become a weight. So I'm saying that I want the linear combination of inputs to be positive for the output to be 1. And if it's negative, the output is going to be 0. So basically, you're saying that the perceptron is basically a sine function applied to this weighted combination, right? So what we want to do, we are given the red and the blue dots. Okay, I've changed my convention, so bear with me. Now the blue dots represent the 1 class and the red dots represent the 0 class, except I'm not calling them 0, I'm calling them -1. Whether I call them 0 or whether I call them -1 is a matter of convention. It will help me over here. So I want to find a hyperplane that perfectly separates the 2 points. Because once I find the hyperplane, my perceptron is simply this unit that uses the weights of this hyperplane as the input weights, right? Now, one thing I want you to remember that I want you to know, do we have a duster? So if I have something of this kind, right, the decision boundary doesn't go through the origin. So what magically happened when I appended a 1 to make this boundary go through the origin? How did this affine function become linear? So what happened is now I'm going to introduce a bias, right? That means the input is now 3-dimensional, right? And my entire input space lives in this plane where the height is 1. Correct? And if the height is 1, now I have all of these minuses over here. I have the pluses over here. On this plane, the output doesn't go, the line doesn't go through the origin, but the extension goes through the origin. Right? The slice goes through origin. So I've converted the whole thing to be a linear function. So, Karthika, are you looking confused? Okay, explain. So think of it this way, right? I just took a sheet and raised it off the ground. So there was this line, but then I can draw a plane that goes through the line. And that plane now goes through origin, right? So it became a linear function, yes. There was somebody else who raised their hand, yes.
So affine is when it goes through the origin?
Affine is when it doesn't go through the origin. Linear is when it goes through the origin.
Okay, so how did you said that we were converting it from an affine function to a linear.
That's exactly what we did. So here, we're saying that the sum must be 0, right? So that's basically, there is no bias term over here.
Okay.
Whereas earlier I did have a bias term, right? So just to get an idea. Now working with linear is just fine, you agree. If I can raise things off the ground, then I can work with linear functions. So now something else. What does this equation really mean? Summation wi xi equals 0. I can write this, can I write that equation as in vector form? If I wrote it in vector form, how would I write it? It's a dot product, right? I can say w equals w1 through wn plus 1, and x equals x1 through xn plus 1, where xn plus 1, of course, is 1, right? And we are saying w transpose x equals 0. What does this equation mean? Anyone? It's the set of all x's that are orthogonal to a w. Correct? So given that, if you look at this line, this is the line that represents the boundary. Where would the vector w be? Perpendicular to it. Basically, w is a vector that's orthogonal to every x on the plane, right? But that's the incorrect way of thinking about it. The plane is the set of all x's that are perpendicular to w. So here's what it looks like. You're going to have this vector w, and this is the plane that is perpendicular by definition to every vector in w. And so the actual equation that we have for this plane is w transpose x equals 0. Inner product between w and x is 0. So now, how can I actually, so again, going back, we want to find this guy given only the red and the blue dots, right? How would we do this? Now here is the, okay. Do I have the, okay, here is the perceptron as we defined it. we said instead of using a 1, 0 notation for the output, I'm going to use a 1 minus 1 notation for the output. Okay, so I can say y equals sine of W transpose X. Right? That's basically exactly what my perceptron is at this point, once I've converted it to a linear function. Now, in which direction must X point for the output to be positive? When is W transpose X positive? What is W transpose X? It's the inner product, right? So W transpose X equals mod W mod X cos theta, where I have W, I have X, and that's theta. Correct? When is cos theta positive? What's the value of theta? It's between minus pi over 2 and pi over 2. Correct? So in general, if this is W, all x's from here to here are going to end up giving you a positive output. All x's below this plane, meaning x's whose components are opposite to W, are going to give you a negative output. Correct? So basically you're saying, I want W. So if I have, now go back and think about it. If I have a training instance, which is a plus, where do I want W to point? Exactly at X. Correct? That's when I'm guaranteed that it's on the positive side. So this is what I want W to be. Suppose I have a training instance which is negative. Where do I want W to point? Exactly opposite to that guy, right? I want, in this case, I want W to point this way. That way you're guaranteed that the inner product is negative. Mean? Yeah? Okay. So the entire perceptron, did that make sense to everybody? Anyone who didn't get that, right? Because the entire perceptron algorithm is based on these two simple notions. A, that W is orthogonal to the plane, and B, for positive instances, you want W to be pointing at the instance. For negative instances, you want W to be pointing exactly away from the instance. And so here is the overall algorithm. We have our set of training instances. We're going to use the +1, -1 convention. And I initialize my W. When I initialize my W, no matter what my W is, I can compute the inner product between my training instances and W for every training instance. Some of them will be classified correctly, right? For those guys, I don't need to do anything. Some of them will be. So the only time I need to actually adjust W is when I encounter some instance which has been misclassified. And for those guys, let's say I have the output, which is the sine of W transpose X for each training instance. And if the output is not what I want it to be, if it's misclassified, how would I correct W? So let's say W is pointing this way, and I have an X which is this way. So it's been misclassified. X is positive. What would I want to do to W? I want to drag W towards X, so that X becomes positive, right? On the other hand, if I've got an X and it's misclassified, and X is of the negative class, what do I want to do to W? I want to push it away from W, right? So the simple rule that we're going to have, Y times X, if Y is positive, you get the same as X, right? If Y is negative, you're subtracting X. You're pushing W away from X. So this is the very simple perceptron algorithm. You only update W on misclassified instances. If the instance is misclassified, for a positive instance, you add the X to W. Basically, you're dragging W towards the instance. If the instance is negative, you subtract X from W. You're pushing X away from you're pushing W away from that instance. So overall, here's what the algorithm is going to look like pictorially. So let's say my blue dots are all my plus ones. The red dots are all my minus ones. I want to learn a perceptron for this particular instance. I can randomly initialize it. If I randomly initialize it, that's my initial W, and that is the boundary that I've got. Okay? All of these guys, let me go through the positive instances first. All of these guys are correctly classified. I don't need to do anything. But then, this one is misclassified, right? So if this is misclassified, what will I do with W? Pardon me? I'm going to add X to W. Basically, I'm going to drag X towards W, right? So that's my misclassified instance. So I'm going to add this vector to W, and now that's going to be my new W. And when that's my new W, what happens to the boundary? The boundary is perpendicular to it. Voila, this gets correctly classified, right? But then now you have this other misclassified instance. It's a negative instance. What are we going to do with W? We're going to push it away from this instance. So that's my vector. I'm going to subtract it from W. That's my new W. That's my new boundary. Everything is correctly classified, right? 2 steps in this case. Although my initial instance guess was so bad that almost half the instances were misclassified. In 2 steps, I finally found a boundary which perfectly separated the 2 groups of data, and I have perfect classification. I have a perceptron. I can just use the weights of this. I can use the components of this W as the weights in my perceptron. And this perceptron is going to do a perfect job of separating the 2 sets of data, right? So there's some very nice guarantees. These guarantees are one of Rosenblatt's contributions was he proved that if the 2 groups of data can be separated by a line, this kind of update will find a solution in a finite number of steps, and that's the beauty of it. It's not going to keep going on and forever, because you are correcting the vector after encountering each misclassified instance. So you might have a suspicion that I see one misclassified instance, I correct my weight, but then the corrected weight vector now goes and misclassifies something that was correctly classified in the past. Now I go back and correct for that. This guy is going to come back. Now this is going to get misclassified. You have this suspicion, vague suspicion, that this can keep oscillating and never really stop. You can guarantee that that will not happen if the data are separable. In fact, you can show that after no more than R over gamma squared misclassification, if I initialize my W with a 0 vector, then after no more than R over gamma squared misclassifications, I'm guaranteed to find a solution, where R is the length of the longest training vector, and gamma is the best case closest distance of a training point from the boundary. So it's the same as the margina in an SVM. Intuitively, we're going to say it takes as many increments of size gamma. It takes many increments of size gamma to undo an error from taking a step of size r. Now, that doesn't make a lot of sense, but let's look at it pictorially, and maybe this will make sense. So here are all these training instances. This is the longest vector, r, right? So in the worst case, what's going to happen? In the worst case, you correct for r gets misclassified in the first instance. So you subtract r in this case, and you correct the weight. But as a result, now it goes and screws up every other training instance, right? Now, here is a decision boundary. This is a perfectly good decision boundary. And this is an optimal decision boundary in some sense. How is it optimal? This is the decision boundary which is farthest from all the training instances. This is what a support vector machine would capture, right? If I actually rotate this decision boundary in any way, it's going to get closer to at least one of the points. So this is the boundary so it has to be exactly midway between the 2 closest points to the boundary. We know this, right? So that distance from the boundary, that's the margin. That is the term gamma. And so you'd have to correct for this gamma. If I make an error due to correcting for this r, then I have to unwind that error by making new corrections. And those new corrections depend on gamma, and the maximum number of corrections I will have to make is bounded by r over gamma squared, which means that for any given training set, there's an upper bound on how many iterations I must perform before I actually find a solution. And this is pretty limited. This is not going to go on indefinitely. It depends only on the arrangement of data points. So it's a beautiful answer. So we find that for a perceptron, where I know there is an answer, I have a bunch of blue points, I have a bunch of red points, they can be separated by a line. In a finite number of steps, I can always find that perceptron. Beautiful, right? Now, let's look at a more complex problem, this guy. So this is the old double pentagon problem that we saw in the past couple of classes. I give you training points. So I'm not actually giving you the pentagons. I'm just giving you the red dots and the blue dots. You're supposed to learn a network that charts out the two pentagons. And in fact, I'm also going to tell you that the network architecture is given to you. I'm telling you that this is actually two pentagons. So that's a lot of information I'm giving you, right? And I'm specifically telling you that here is one network. This is going to capture one pentagon. Here's another subnet. That's going to capture the second pentagon. And I'm going to OR the two. This is the architecture of my network that I'm specifying to you, right? And so if I'm specifying all of this information, what else am I specifying? I'm telling you this final output is an OR. I'm telling you that the thresholds here and here are 5, right? So I'm giving you a whole lot of information. And I'm giving you the perceptron learning rule that we just saw. Can I learn this? And if I want to learn, so what do I mean by learning this? I need to learn for each of these guys these lines, correct? That's what I mean by learning this. So given the perceptron rule and this training data and a perfect architecture, how painful would it be to actually learn this network? Anyone? What would the process be? Yes?
I would start by going perceptron by perceptron, but I don't think you can do it because they're never linearly separable, right? So if you try to draw a line somewhere, you could never get perfect linear separability in that perceptron.
Okay, so?
I don't think you can do it.
Anybody else?
So you need to know the labels for like one line?
Okay.
Like,
but yes.
No, I don't actually.
Okay, yeah.
Shouldn't you be able to do it because you can assume that the left side will learn the upper pentagon, the right side will learn the lower, and the individual neurons are actually learning those lines. So we learned in the last class the area within it, if it is 1, you will be able to learn that. And
yeah, but
you're just combining the two, right?
But if I'm just giving you the perceptron rule, the data have to be separable, right? How do I learn?
It is, separable in,
How do I learn individual neurons? Yes.
Can you possibly change the labels of?
Thank you. Correct. So I need to learn these guys, right? So consider a single line. If I want to learn this, I have to change those labels to this guy in order to be able to learn that line, right? But do I know how I must change the labels? I don't, right? And mind you, that means I must also learn how to change the labels for each line. And how many of them do I have to? So this is basically what I've got to do. This is the data I have. And the only way I can figure out how to change the labels is to try out every combination. I'm going to take every blue, flip it to a red, and then try to learn a line, right? Eventually, I will be able to learn a line. But there are many such combinations which will give me lines, correct? I can change those blues to reds in many different ways, and I will get different lines. But not all of them are the line I want. I want specifically this guy. Make sense to you, right? This means I must simultaneously learn how to change the labels for every one of these 10 lines such that when I add them up and pass it through the rest of the network, I get the target function, right? Is it computationally, is it theoretically feasible? Yes. Is it computationally feasible? No, right? It's an exponential search. And so, basically, this is where things were stuck for a very long time. We must know the output of every neuron for every training instance in order to learn the neuron, even when I gave you the perfect minimal architecture and a problem that is learnable. Right? So basically, because if I get just one instance mislabeled, I'm going to learn the wrong line, I won't get the pentagon. So I have an exponential, super exponential set of combinations. One of them is right. And I have to search through all of these guys to find that one fellow so that I can find the solution, but it exists. And if I had infinitely fast computers, I could do it. We don't have infinitely fast computers, right? And the problems get much more complex than this. So this whole thing is basically NP. It's NP in the sense that if I give you the answer, if I propose an answer, it's easy for you to verify it. But it's infeasible to actually come up with an answer. So you can't, although you can train this entire network using just the perceptron rule, it's theoretically possible, it's computationally infeasible. And this is where things were stuck for a very long time. This was, Minsky came along, Rosenblatt came along and said, I can learn a perceptron. Minsky said, you can't. Here's an XOR. This is not going to happen. You could do it if you actually network these guys. Then you go back to the perceptron and say, well, I can network these guys. In theory, I can learn it. It's practically infeasible. Let's go back and do simpler stuff. And things stayed there for a while. But then maybe we can use greedy algorithms to do this, right? Meaning, is there some way of beginning to correct things incrementally and still hope to come up with a solution? These were algorithms called Adeline and Madeline, proposed by Bernie Widrow, who's, how many of you have heard of the Widrow-Hoff learning rule? So everybody has heard, if you haven't heard about it, everybody who's done any machine learning has used the Widrow-Hoff learning rule, which is very similar to the perceptron rule. If you're learning some parameter theta, you're going to say f of x. It looks something of this kind. Basically, for any x, you have the current output of the function that you're trying to learn. Here's the desired output. This is the input. So this is the error. You multiply the error by the input. And this tells you how much you must correct your current estimate for the parameters. And you've done this. I mean, if you've done machine learning, you've done this everywhere, pretty much everywhere. This is the standard learning rule we use all over the place. So this was by Widrow. It's the Widrow-Hoff rule. I won't go over it, but Adeline and Madeline are discussed at length in the slides, and they appear in the quiz. So please go over the slides. Right? Let me get on. So here's the story so far. Quick summary. We said learning a network is the same as learning the weights and biases to compute a target function, if you have a network with sufficient capacity. In practice, we're going to learn the networks by fitting them to match input-output relationships of training instances drawn from the target function. And a linear decision boundary can be learned by a single perceptron. We saw that. Non-linear decision boundaries require networks of perceptrons. Training an MLP with the threshold function activation perceptrons will require the knowledge of the input-output relationship for every training instance for every perceptron in the network. And since you won't be given this when you're training data, if you want to learn these networks using threshold activations, basically you end up with an NP-complete combinatorial optimization problem. Right? So the realization that training an entire MLP was a combinatorial optimization problem basically stalled development in neural networks for almost a decade, maybe more. So why do we have this problem? People went back, and in fact, in the early 70s, guys, who was the one who first came up with the backprop, Ryan? Pardon me? No, it wasn't Hinton. This was the guy in MIT, 1972. Paul Verbos, right? So Paul Verbos had a PhD thesis where he proposed an algorithm called backpropagation in the 70s. But it sat there for a while till Hinton, who was then at CMU, revisited the backprop and introduced it into training neural networks, and then it became all the rage. So how many of you are aware that Hinton actually built his career here at CMU? Some of you? He was here for, I think, until 93 or thereabouts. And he continued to have PhD students in CMU for several years afterwards. So anyway, let's go back and look at this. Why is learning an MLP so hard using the perceptron rule? So to look at this, let's look at this training data, right? Here are all the red training instances and the blue training instances. And let's say I have this dark red line as my current guess for the boundary that basically specifies the weights. I know it's wrong. I can go through my data and I can say that I've got some instances which are misclassified. Now I say, okay, I've got to change my weights. If I change my weights a little bit, am I moving in the correct direction or not? Am I moving towards the direction of which is likely to improve matters, or am I making things worse? Can I deduce that information from a unit of this kind? Really no, right? Why? Because the output is a sine function, right? I can keep changing my W for a whole lot, and the output won't change. And then at some point, I'm going to cross one of my training instances, and that's the only time my output is going to change. So basically, because I'm using a sine function, I can keep modifying W. I can basically, what I mean is this W, I can take this line and swing it around to all of these other red lines. And the overall output of the function is not going to change on any of my training instances, right? So in other words, simply by moving my W around, I cannot figure out whether I'm moving it in a direction that's appropriate for improving my performance or making it worse. Make sense to you guys, right? So this is the key piece. This is basically what we're going to hang everything off of. And so when you get to larger problems, this is actually this becomes much worse. That was just for one perceptron. So over here, I could propose some initial weights for this guy. I have something like so. And then I know the output is wrong. The network is fairly complex. Even if every other perceptron has got the correct value, here, if I change the weights a little bit, is the overall output of the function getting closer to what I want or not? There's no way of finding out because the output is a step function. The output will stay constant till you cross a training point, right? So small perturbations of W give you no idea of what is really happening to the output. And that's the fundamental problem, why the perceptron rule could not be applied. So there's a second problem. We assume that the data are all nice and linearly separable, right? That's not what's going to happen. I mentioned noise. So what exactly do I mean by noise? Your data are going to look more like this, in the sense that you have some blue dots in the red region, or is it red dots in the blue region? There's really no way of saying, right? It's a matter of how you skew your eyes. Meaning now I cannot draw a line or a hyperplane which separates the blue dots from the red dots. In this case, the perceptron rule is not even going to work, right? So solution, I'm going to make the neuron differentiable. What do I mean by differentiable? My basic problem was that when I changed my weights a little bit, it didn't tell me whether the output was getting better or not. And this is because I used a sine function. I had this threshold function, which wouldn't change for large changes in W. So I want to change my activation function such that if I change my W, I get an immediate indication of whether things are getting better or not, right? If I have some way of indicating whether things are getting better or not, then it's easy. I'm going to wiggle it a little bit, and if things are getting better, I'm going to continue wiggling it the same way. If things are still getting better, I'm going to continue wiggling it the same way. If things get worse, I go back. So I get immediate feedback that I can operate on, and now I can actually learn the parameters of my network. So you want to have, that means this activation function. Instead of having something like this, you want to have something smoother, where changing the weights of the network changes the output in a kind of smooth way and gives you an indication of which way the output is headed at each of your training instances. And that tells you in turn whether things are getting better overall or not. And then you can use that to learn your network, right? So we're going to make these, the threshold function is not differentiable. What I mean by not differentiable is, in this case, the derivative is 0 pretty much everywhere except at one point where the derivative is undefined. That was the problem. Instead, we're going to have a function of this kind which has a non-zero derivative pretty much everywhere, or at least is differentiable everywhere. So this guy, for instance, has 0 derivative to the left, but it's still differentiable everywhere, or almost everywhere, right? So we're going to have to replace it with differentiable derivatives. Now, differentiable activation functions. So there are various activation functions that we could use. Of these, this sigmoid has a very specific and very useful interpretation. So it actually gets and ends up being used a lot. The sigmoid has this form. First, you compute the affine combination of the inputs. And then once you compute the affine combination of inputs, the sigmoid is just 1 over 1 plus e raised to minus z. And you can see what happens. If z is minus infinity, this becomes infinity. The output is 0, right? If z is plus infinity, e raised to minus z becomes 0. The output becomes 1. And in between, the transition is smooth. So the sigmoid is going to have a shape of this kind, like so. Now this has, what is the useful property? What is the, of this kind of function? It has an interpretability about it that we're going to use, which is this. Let's say here, I'm going to use a simple two-dimensional example. So in your training data, it's two-dimensional training data, you're going to have some reds on the blue side, some blues on the red side, right? So if this were the decision function that you wanted, this is the line, the output is 1 to this side and 0 to this side, your training data includes some red dots suspended above the blue region, and it has some blue dots hung on the floor, fallen on the floor in the red region, which means that now you don't really have separable data and your perceptron rule doesn't really work. So let's look at this from a one-dimensional perspective. On one-dimensional data, this is going to be x, and those are the y's that you want. So you have a bunch of blue points where the y value is 0. I keep flipping the colors, bear with me. Okay. So you have a bunch of blue points where the y value is 0. You have a bunch of red points where the y value is 1. A perceptron, standard perceptron, is going to be a threshold function. Is there any threshold function that cleanly separates the blues and the reds? No. Not really, right? There isn't. You cannot. But then let me change my view. Let me look at a small window around the leftmost point. And instead of plotting just the value of that point, I'm going to plot the average value of all of the points in that small window. Okay? And I scan this window left to right. As I keep moving right, the average value is going to remain 0 till I encounter the first red point overlapping the blue points, at which point the average value is going to go slightly off 0. And as I keep moving right, the average keeps going up, and eventually I get to a point where there are no more points on the floor. All the floor points are at 1, and now the outputs are all 1, right? So if I were just to take a small window and slide it left to right, and compute the average value of the outputs within that window, technically what am I computing? I'm estimating the fraction of points within the window that are 1 for that particular value of x. Alternately stated, I'm estimating the probability of 1 for each x, right? And as I go left to right, initially the probability of 1 remains 0, and then it begins going up and then slides up to 1. And so if I connect that whole curve, you're going to get something of this kind. That's your sigmoid, right? Turns out, so this is just p of y equals 1 given x. And the sigmoid function that we saw is actually a very good fit for this kind of thing. So in 2 dimensions, this is what it would look like. It would look like, so if x is a 2-dimensional variable, the sigmoid function is going to look like this. But then it's still a linear classifier. What do I mean by a linear classifier? this is the probability of y equals 1 given x. So that's only a probability, right? If I must take a decision, I have to say if that probability exceeds 0.5, I'm going to call it a 1. If the probability is less than 0.5, I'm going to call it a 0. If I did that, then I would choose a threshold like 0.5. Or I could be more conservative. I'd say if the probability is greater than 0.6, I'll call it a 1, otherwise I call it a 0. Regardless of the threshold I choose, if I take the locus of all the values on this, all the values where the sigmoid actually gives you a probability of exactly that value, say 0.5, that's still going to be a line. So it's still a linear classifier. But the actual function is continuous. Basically, the function is going to be something like this. So this where the vertical axis is the probability of 1. And if I set a threshold, meaning if I slice it at any point, the outline of the remaining slice is going to be a hyperplane or a line in this particular case. Okay? So we'll revert to the fact that perceptrons with sigmoidal activations actually model class probabilities in a later lecture. But for now, moving on. So let's go back. Here's what we got. We have a perceptron. And if I use a differentiable activation function over here, then what does differentiability mean? We're going to spend some time on going over calculus. And I'm running behind, but that's okay. So if I have a function of this kind, right? And let's say sigma over here is differentiable. What are we really saying? What this means is that I can tell you how much y will change if I change x by a little bit, right? When I say it's differentiable, I'm literally saying I can compute dy over dz. I can compute this, right? So basically you have z, you have y, whatever the function may be. I've just drawn a sigmoid. And at any z, I can say this is the corresponding y, right? So then I can ask myself a question. Over here, if I just change my z by a small delta z, what is the corresponding change in y going to be? And that's going to be, I can just read this guy out. That's going to be here. And this is going to be my delta y, right? So this ratio, so for differentiable functions, I have a formulaic way of saying if I change my z input a teeny weeny bit, what is the corresponding change in the output going to be, right? But then this guy, z in turn, is a weighted combination of the inputs, right? So now I can say if I change my w a teeny weeny bit, how much will y change? I can compute that too. Because if I change my w a teeny weeny bit, I know what the corresponding change in z is going to be, because z is just a weighted combination of w's. And so I can tell you what the corresponding change in y is going to be. So in other words, the output of the perceptron is differentiable with respect to all of these weights. And so also, the output of the perceptron is differentiable with respect to all of the x's, because x's and w's are symmetric. Make sense to everyone, right? Questions? No? Because this has a very deep interpretation, right? Here. Y is differentiable with respect to all of these weights, which is great, but it's also differentiable with respect to all of the outputs of the neurons in the previous layer, which means I can tell you how much a small perturbation of these guys is going to change y. But by the same token, these are differentiable with respect to these weights. So I can tell you how much a small change of this weight is going to change this guy, but I know how much a small change of this guy is going to change this guy. So overall, I can tell you how much a small change in this weight is going to affect the final output. And similarly, I can tell you how much a small change in the output of this perceptron is going to change this output. And therefore, I can tell you how much a small change in the output of this perceptron is going to change the final output. Working my way backwards, I can tell you how much a small change of any parameter in the network is going to affect the output. I can also tell you how much a small change of any input to the network is going to affect the output. So this entire network now becomes differentiable with respect to all of its parameters and all of its inputs. Right? So the overall function now is differentiable with respect to all the parameters of the network. And this is what we're going to use. Now let me go back to this overall setting for learning a multi-layer perceptron. The overall setting was something like this. You're given a set of input-output pairs, training pairs, where for each input x, you have the corresponding desired output, d. Inputs and outputs may both be vectors. And we want to find the network parameters, which are the weights, such that the network produces the desired output for each training point, or at least a close approximation to it. And we are assuming that the architecture of the network is specified by us. Now go back over here to this figure, to the figure on top. If the network is inappropriate for a given function, can I still come up with a good approximation? I just minimize that error, right? It won't be perfect, but I can still come up with a good approximation. So that's basically what we're going to use. So let's go back to my function, to this problem here. So this is what we wanted to actually minimize, the total error. But that doesn't really make sense. Why? Suppose my network is, so if my network has got the capacity to learn this function perfectly, no big deal. But if my network is lacking even in a little bit in the capacity to learn this function perfectly, right, then does doing something like this make sense? Let me give you the context first. Suppose I know that in real life, x values only occur in this range. Real life, our input never exceeds that range. Does it make sense for me to try to minimize the error everywhere? No. I just need to focus on this region, right? Now, suppose I tell you that in real life over here, this range of x's occurs much more frequently than these guys, and these guys never happen. Then how must I correct myself?
You should try to be as accurate as possible.
I want to focus more on where x's are more likely to happen and less on x's where x's are less likely to happen, and I can ignore the regions where x's don't happen at all, right? So in other words, what I really want you to do, can you shut your laptop, please, Yanda? Yes, thank you. So what I really want you to do is, this. At each x, I'm not just minimizing this overall divergence, I'm weighting it by the probability of that x, right? Things that are more frequent contribute more to the overall impression of error. Things that are less frequent contribute less. So what is this term over here? It's a statistical expectation of the divergence, right? So this is so basically, I want to find the W that minimizes the expected divergence over the entire input space. Make sense? Right? So far so good. But here's the issue. What did I do? Okay. We don't actually have the entire function f of x. We only have a bunch of samples. We saw this. This is an old slide, right? We just have those input-output relationships at specific points. So in other words, we cannot actually compute this term. But what can I do? I can compute the average error on all of my training points. Now the average error on my training points is going to actually be a good approximation for the expected error. Why would that be? So long as my training points are actually drawn from the real distribution of the data, this should be just fine, because I'm defining my error as 1 over n summation I divergence between f of xi w and the desired output at that x. If I take the expectation on both sides, basically, what do I mean by taking the expectation? Just taking the statistical. In this case, what this means is that if let's say I equals 1 to n, right? I have drawn some n training points, and I've computed the average error over those n training points. If I repeat this process a bajillion times, where in each experiment I draw n training points and compute the average error, what is the average of those averages going to be? That is what the expectation means, right? So, let's say my first run I got these 4 training points. I'm going to have some average error over these guys. In the next run, I got these 4 training points. Over those 4 guys, I'm going to have another error. And then in the next run, do I have more chalk somewhere? White. Yeah. I got these 4 average training points. Over those 4 guys, I'm going to have those 4 training points. Over those 4 guys, I'm going to have some other average error. So for each set of n, I have an average error. On that set, I take the average over all of those averages. What does it look like? That is the statistical expectation of the average error, right? This is going to be by linearity just 1 over n summation I expected value of the divergence. This is not a function of the specific input. This is an expectation. So this is simply going to be 1 over n times expected value of divergence, which is the expected value of the divergence. So in other words, this estimate that I've got over here, on average, is going to be the same as this guy. If I generated n training samples many times and took the average error over all of those different runs, I'm going to end up with the same. I'm going to get the same as the expected error over the entire training set. So I can hope that if I minimize this guy, in some sense I'm minimizing this other term. Again, there's no guarantee, but there's reason to believe that one maps onto the other, right? I'm going to run a few minutes over. Please bear with me. A couple of minutes, okay? So given a bunch of training points, we're going to define an error on each training instance, which is the divergence. You compute the average error over the entire training set, and you want to find the weights W that minimize this average error over the entire training set. This guy is the empirical error. This is the expected error, expected divergence. This is the empirical average of the divergence. We'll also call it the empirical risk, just to, machine learning terminology. We will sometimes call it this, although as far as we are concerned, it's just the error. The empirical risk, it's an empirical approximation for the true risk, which is the expected divergence. And it's actually an unbiased estimate in the sense that if you take the expectation of this guy, you actually get the true risk, right? The true error. And so what we are really going to be doing is this. Given a set of training instances, you're going to be computing the empirical error, average error, over the training instances. And you will find the W. This is a function of the weights, right? If I change the weights, the output of the network changes, the error changes. And you're going to try to find the W that minimizes this error. So this is a function of a problem of function minimization, or rather optimization. So the story so far, we learn networks by fitting them to training instances drawn from a target function. For threshold activation functions, this becomes a combinatorial optimization problem. So we use continuous activation functions with non-zero derivatives to enable us to estimate network parameters. And we define a differentiable divergence between the output of the network and the desired output for the training instance. Again, the divergence must be differentiable, because if it's not, the whole thing collapses. Even if the network is differentiable, if the definition of the error is not differentiable, then there's no way for us to say, if I change the parameters of this a little bit, did the error go up or not? So if you begin counting errors, right? Like how many times did I misclassify? Is that differentiable? Counting is not differentiable. So we need a differentiable divergence function. And we optimize the network parameters to minimize this differentiable divergence function. I'll stop right here. We'll pick up from here in the next class. Questions? No, thank you.